Hey guys, Mr. Larson. Just wanted to run you guys through 3.2, which is our intro to logs. We'll start with doing graphs of logs, show that they're inverses of exponentials, and then we'll talk about transferring between log and exponential form, and then evaluating and solving log expressions and equations. Okay, so first thing I want you to do is the warm-up A, B, and C. Go ahead and pause, and then you can hit play when you're done. Okay, you can see our answers there. And then next there's two two graphs underneath. Go ahead and try those. Same thing. Actually, you know what? I'll walk you through those. That's what I'll do. So for this first graph, we're graphing the function y equals 2 to the x, and then the second one we're going to do y equals log base 2 of x. Okay, so I went ahead and I sketched y equals 2 to the x, and I filled in the key features. So I did a simple xy table. I went from -2 to 2, right, over here for the x values, just plugged them in, calculated the outputs, sketched those points, and then drew my graph, and you can see my key features that I've done there. Okay, I know you guys are capable of doing that, but go ahead and get that down. If you need to pause, you can. And then let's talk about y equals log base 2 of x. So this is going to be the inverse of the graph that we just did, y equals 2 to the x. So remember, inverses, you're taking your x's and y's and flipping them, right? So I'm just going to go point by point, and we're going to switch the inputs and outputs. My daughter's napping upstairs. She doesn't understand, well, she's supposed to be napping. She doesn't understand the concept of screencast time. So she might be singing in the background. That's okay. That's okay. All right, so let's go ahead and plot these. So 4, 2. Okay, we can connect. That's not going to hit the y-axis. Okay, so I drew it a little off. But remember, our domain and range are going to switch, which you can see from the graph. So remember, if these were on the same graph, we would see that these are basically a reflection over the line y equals x, right? So that serves as your mirror. Inverses reflect over that. Okay. All right. So if you can graph the exponential, you can graph its inverse, which would be the log form. So in general, if I use, instead of a known base, if I have a variable, the inverse of y equals b to the x should always be y equals log base b of x. And if you want to write down how we're saying that, it's log base b of x. Okay, a lot of people aren't sure how to say it. That's how you can say it. So transformations, you guys have done transformations. We've tested you on this. You've done it in years past. So for each of these, I'm not going to walk you through everything, but what I will say is these are all based off the parent function y equals log base 2 of x, which we did in the warm-up. So just notice that negative there, right? That's going to be a reflection. This +3 will be a shift, right? A translation. This +1 will be a translation. So I'll kind of walk through the first one here. Let's start with our XY table. And that negative is going to be a reflection over the x-axis, right? Over the x-axis. It will affect our y values. So from my log base 2 of x graph, let's look at our table, and I'm going to reflect, or I'm going to multiply all of my y values by -1, right? So it'll be 2, 1, 0, -1, -2, and my x's stay the same, right? So 1/4, 1/2, 2, and 4. And we can sketch that graph. That's not right. Come on, Mr. Larson, act like you've been here before. 2. Okay, and we should see that that was a reflection over the x-axis from our first graph. Okay. So if you want to try the last two, I would number 2 and 3, go back to the original XY table and modify by this +3 and this +1. Okay, so think about what those translations would be. So go ahead and pause, try it, and then come back. Okay, so there you go. First one or second one's translating up 3, third is left 1. And remember, these are modifying the original parent graph from the warm-up. Okay. All right, so now let's get into some operations. So converting between log and exponential form. This is really crucial, especially when you're solving equations, and it's good to know like how these two are related to each other. So if you have something in the form in blue here, a to the x equals y, we can change that to log form. It's the exact same thing as log base a of y is equal to x. Okay, so notice where the variables are moving to from the first one to the second one. There's a couple ways to remember how to transfer between these two forms. Somebody a few years ago taught me drop and swap, which I think is a term that's used in like your Spanish classes or world language classes, but I kind of like it for log form, or for converting between these two forms. I shouldn't have drawn that yet. Okay, so drop and swap. So first we drop our a. And then we swap these two variables positions, right? So log base a of y is equal to x. So if you look in red there, I know it's hard to see, but it should match up with what you see here. Log base a of y is equal to x. It also works the other way too. So if I want to go back to exponential form, I drop my a, and then I swap my x and y. A to the x equals y. So I'm dropping, and then we are swapping. Okay, so drop and swap. Okay, so let's practice that. So log base 4 of 16 is equal to 2. That's a true statement, and we can see it probably a little more clearly when we're in exponential form. So let's go ahead and change it to exponential form. So I want to drop my 4. And then we will swap the 2. Oops, I should do that in black to stay consistent. Swap the 2 and the 16. So 4 to the second power is equal to 16. I'll write that again. Okay. I'll stop with the green and black sketches, but this would be, let's see, drop my 5, swap my 3, and my x. So 5 to the third is equal to x. All right, last one, log, drop my 4, swap my 64 and 3. So I would literally just practice that. You can come up with any log or any exponential and just practice converting to and from. It doesn't have to be even a true statement, but just so you get used to where those are going. Okay. All right. So two types of logs that we're going to see very, very frequently. Maybe I should have wrote the common log first. It's usually the most common one that we see, which is why it's called the common log. But it's the one that we have a base of 10. Okay. If you have log base 10 of x, a lot of times we don't even write that 10 because it's so common, right? So it's kind of like not writing the 1 before your variable if the coefficient is 1, or not writing a 1 as an exponent. we still know it's there. So if you ever see log of x with no base, the base is 10. It is the same thing as log base 10 of x. You can change it to say log base 10 of x if you prefer that. That's totally fine. So we would pronounce this as log of x, right? If it just says log x. Second one is our natural logarithm. So that's when you have a base of e, log base e of x. We call that, we write it as ln x, and that's a natural log of x, all right? So let's evaluate some logarithms. Okay, so here's how we can evaluate logs. If I have log base 2 of 64, I want to see what that's equal to. I want to find the value of that. So first thing I would do is set it equal to your favorite variable. I usually use x. Just make sure it's a variable that's not currently in the problem. So I don't have any variables yet, so x is fine. So what I want to do is transfer this to exponential form. So drop, swap. 2 to the x equals 64. You can do trial and error on the calculator. This would actually probably be a non-calculator problem, so I can get the same base on each side. Let's see, 2, 4, 8, 16, 32, 64. I think that was 6 times. So 2 to the x equals 2 to the 6th. So I can say that x is equal to 6. I guess technically you don't need that x equals because it wasn't part of the original, but that equals 6. All right. Log base 8 of 1. Again, let's set that equal to x. 8 to the x equals 1. Well, the only way you're getting 1 as an output from an exponential term is if the exponent is 0, right? So that x there has to equal 0. Okay, drop and swap. 7 to the x is equal to 7. Well, let's put a variable, or let's put an exponent there. Exponents have to be equal now, so x has to equal 1. All right, I think you guys are starting to get it, right? This is log of 1,000. It's really log base 10, so we can fill that in. Let's set it equal to a variable. Now I drop and swap. 10 to the x equals 1,000. Let's get the same base on each side. So 10 to the x equals 10 to the, say I have 3 zeros, so 10 to the third, and that is equal to 3. Log of 1,000 is equal to 3. Right? 3 to the x equals 1/9. 9 is 3 squared, right? So this 1/9 is really 1 over 3 squared. And remember, I can move that to the numerator by switching the sign on the exponent. So 3 to the x equals 3 to the negative 2. Well, that x is equal to negative 2. Okay. Okay. If you guys haven't been able to tell already, there's definitely going to be a part 2 of this, but that's okay. It should be pretty quick. So for number 6, remember, anytime you have ln, that's log base e, right? So this part is log base e. Now I have another e because it's inside the log, right, of e to the third. So again, I'm going to do drop and swap. So e is equal to x. E to the x is equal to e to the third. I have the same base, so I can say x is equal to 3, and we're done. Okay, so make sure just because you have an e inside of the log, you can also have a base of e, right? That happens sometimes. Just like number 3, I had a base of 7, and then I had a 7 inside my log. That's totally fine, right? Okay, so 7, 8, 9 are calculator problems, are the only ones on here that are calculator. And I think you can see my cursor here. Log is the common log, so that's log base 10. That's what we use for number 7. 8, log base e of x, that's really, I'm sorry, of 6. That's really natural log of 6. So I would use ln, which is next to the 4. Number 9, the same thing. So we're literally just going to do log of 200. I know you can't see these. I'll show you the answers in a second. Then I would do natural log of 6. And the last one, natural log of 48. So let me move those so you can see. That's it. So you just do 3 decimals after, 3 spots after the decimal. So 2.301, 1.792, 3.871. All right, guys, I'll see you for part 2. Like I said, it should be relatively quick.